Medtronic technologies impacted more than 72 million people in the last year, equating to 2 people every second. Harnessing the power of technology to take healthcare further, each technology has unique benefits designed to serve patients. The goal of this program is to get closer to the patient and delve into the challenges and impact of each technology in practice. This is the Medtronic MedEd Learning Experience. The INVOS monitoring system should not be used as the sole basis for diagnosis or therapy and is intended only as an adjunct in patient assessment. The contents and conclusions of the following programs are solely those of the speakers unless otherwise cited. The speakers are responsible for all content and any necessary permissions. The speakers receive funding from Covidien LP, a Medtronic company, for this speaking engagement. Medtronic's medical education programs are offered to provide attendees education on FDA-cleared indications and use of our products when applicable. For this segment of the series, a discussion on the utility of the INVOS system. How does spectroscopy work with a focus on the INVOS technology? To help answer this question is Eli Coleman, Senior Research Manager at Medtronic.
First, let's start with why cerebral tissue oxygenation monitoring is useful. Percent oxygen saturation measured at the capillary beds provides insight into changes in organ tissue oxygen delivery due to such things as blood flow changes and vascular resistance and oxygen demand. It also provides real-time information of oxygen supply and demand, which is crucial for guiding treatment decisions to prevent cerebral injury. Alternative methods for measuring cerebral oxygenation include monitoring jugular venous oxygen saturation and measuring brain oxygen tension. NIRS has advantages over these alternative methods in that it is non-invasive and provides continuous monitoring of the capillary beds where oxygen exchange is taking place. INVOS was first to market with NIRS technology in 1996 with the 3100 system. The curves in this graph on the right represents the magnitude for which an atom or molecule absorbs incoming light as a function of wavelength or color. In this graph, we are looking at oxygenated hemoglobin, which is the red curve, and deoxygenated hemoglobin, which is the blue curve, and their absorption behavior across a range of wavelengths of light. By way of an example, imagine you had a glass of just oxygenated hemoglobin, and you had a flashlight that's shown at exactly 650 nanometers. The glass of oxygenated hemoglobin would let that light pass through relatively easily, since the red line is at 650 nanometers is relatively low. In contrast, a glass of deoxygenated hemoglobin would absorb much more of that light. The blue line is at 650 nanometers is relatively high, and we wouldn't see much light exiting on the other side of that glass. We call the loss of light intensity from absorption attenuation, and is governed by the equation seen here called the Beer-Lambert law. From this equation, you can see that the concentration C can be determined by knowing the ratio of initial light intensity, I sub 0, to measured light intensity for a certain wavelength, the absorption coefficient, epsilon, which is the y-axis on the graph, and the path length of light through the medium. In blood, we have a mixture of these two molecules. So when we shine our special 650 nanometer flashlight through a glass of blood at some saturation, the attenuation might be somewhere in between the blue and red curve. And our Beer-Lambert equation for attenuation is due to 2 concentrations. So if we wanted to know the absolute concentrations of both oxygenated hemoglobin and deoxygenated hemoglobin, we have 2 unknowns in one equation. So we add another flashlight at a second wavelength to create another equation, and thereby getting 2 equations and 2 unknowns. And we can solve for the absolute concentration of each molecule. Now, which wavelengths do we choose? For INVOS, there are 2 wavelengths used in RSO2 calculation. The first wavelength is a more red wavelength around 730 nanometers. We'll call this the investigative wavelength. This is chosen purposefully and after careful experimenting with many different options. At 730 nanometers, there is a fairly large distance between the blue and red curves, meaning we get good resolution as various saturations move between these 2 lines. Also, critically at that wavelength, there is a gradual slope in the red curve and a slope of 0 at the bottom of that bump in the blue curve. This is important as we can use LED with a specific mean wavelength of light, but there's variation in that wavelength in reality. So a point around 730 nanometers is less sensitive to those variations. The second wavelength chosen is what we'll call the reference wavelength. Unlike pulse oximetry, that can extract a pulsatile signal to normalize for changes in optical intensity due to things like blood volume, RSO2 measurements are taken at sites without pulsatile flow and sometimes no flow. INVOS uses the intersection point of the absorption curves at around 810 nanometers for normalization. This is called the isosbestic point, which is in the IR region, infrared region. At this point, the attenuation doesn't give additional clues on how saturation is changing, but it does represent the total hemoglobin content, which is the denominator for RSO2 calculation, as well as total blood volume more generally. Also note that these two wavelengths are relatively close to each other. Not shown on the graph are non-hemoglobin chromophores present in the tissue, such as melanin, with their own absorption curves. Proximity between the wavelengths helps ensure that attenuation is affected similarly by these additional absorbers. Let's take a moment and visualize how light at these two wavelengths are affected when passed through various levels of blood oxygen saturation. First, consider scenario A, where we have highly oxygenated blood. High levels of oxygenated hemoglobin results in an absorption curve that's similar to the dashed red line shown in the graph. Note the lower absorption in the red wavelengths. That means that as red light passes through this highly oxygenated blood, we see little change in light, which is graphed on the right side of the page. IR light, on the other hand, has relatively more absorption and is graphed as such and shown as length A. Compare that with scenario B, where we have low levels of oxygen saturation in the blood. Here we can plot the absorption curve as the blue dotted line and see that the red wavelength will have more absorption, more than IR light, noted as length L in the graph on the right. In fact, since the IR wavelength is chosen as the point when absorption is independent of oxygen saturation, the IR light changes the same amount as in scenario A, noted again as length A in the graph. Now we can start to see that the difference of absorption between the red and infrared light correlates with changes in oxygen saturation. And now we can experimentally determine oxygen saturation as a function of red light absorption compared to infrared light absorption. Let's take it one step further to illustrate the importance of the reference wavelength, which again is the infrared light. As Beer law tells us, the more blood we're measuring, the greater the light loss. In other words, if we have the same oxygen content, but the blood volume changes, we may introduce error. But by choosing a reference wavelength that is independent of oxygen saturation, we can normalize out for these changes in blood volume. Scenario C here is the same scenario as scenario B, but with greater blood volume. Note that the difference between red and IR light signals is maintained, even as blood volume has changed. So up to this point, the discussion has been focused on an idealized scenario. In reality, tissue is considered a scattering medium, meaning that there is not only light loss from absorption, but also loss of light due to scattering. The modification to our physics is beneficial for reflectance-based measurement, which means that light will bounce back up to the surface that has reached deeper tissue. The figure on the left shows the density of photons in this banana-shaped path through a scattering medium from a light source to a specific location, a certain distance away from that light source. We call the highest density path the mean photon path, and it reaches a depth of about 1/2 the distance between the entry and exit points. When considering organ tissue monitoring, such as cerebral tissue, we need to acknowledge yet another layer of complexity, this time a literal layer. Superficial tissue above the tissue of interest contains blood vessels, bone, lipids, and absorbing media that will contaminate the measurement of blood oxygen saturation. Next, we'll look at how INVOS overcomes this challenge.
Please tune in next week for a new segment from this series wherever you find your podcast. This is the Medtronic MedEd Learning Experience. Thank you for listening.